Okay, welcome to lesson 22. This will be the A part. I think this is going to be a fairly long one. It's certainly a little bit more thought consuming, and I imagine we will have to, this is one that you may have to watch more than once. So I'm going to try to be as clear as I possibly can here and as thorough. Okay, so today we're going to talk about solving the three types of Moody problems. And the first thing that I want to do before I get into how to solve these is how do I know that I have a Moody problem? So the Moody problem goes back to this Darcy-Weisbach equation. So basically, you've got the energy equation, and as part of that energy equation, right? Like I'm not really concerned right now with all of these other things. Right now, I'm thinking about this head loss, okay? And as part of that head loss, we can split this out into HF, okay? So that's the friction loss along the pipe, plus H sub L, where H sub L is the minor losses. So at the moment, we don't really know how to deal with these minor losses here. Okay, so we're not going to deal with the minor losses yet. But this H sub F, which somehow, okay, so that H sub F, okay, has to do with this Darcy-Weisbach. Okay, so that equals F L on D V squared on 2G. Okay, so you have a Moody problem if you need this F. Okay, so basically, anytime you've got a friction loss along the pipe, you're going to need to solve for this F, unless it's given, which it usually is not. And if you need to solve for that F, then you need to use the Moody diagram, which I have right here. So this is the Moody diagram. Okay, and this one, again, this is the one that comes from the FE equation sheet. Okay, so when that happens, okay, and I want to back up or a little bit, not even more, but I want to kind of dive forward a little bit, and I want to look at this Moody diagram. Okay, and it looks like instead of zooming in on it, I'm kind of enlarging it. But I want to remember what it is that we're looking at here. Okay, and there's a few things that are really important. One is this relative roughness. Okay, epsilon over d. Okay, let's see if I can write on it. This is epsilon over d. So epsilon is the roughness of the pipe, or the size of the roughness elements, and d is the diameter of the pipe. The Reynolds number over here. Okay, that's Vd, so that's the velocity in the pipe times the diameter of the pipe divided by the viscosity of the fluid. And then this friction factor, which is the thing that we're looking for. Okay? So, in light of that, okay, let's shrink this. And let's think about, can I shrink just the Moody thing? Come on, there you go. Okay, and what we want to do here, and nobody ever did this for me when I was taking this course, but I think it's good to think about this in terms of what they call the three types of Moody problems, okay? And so it depends on what you're looking for, okay? So in type 1, okay, given epsilon, okay, so that's the roughness elements of the pipe, okay, the diameter of the pipe, this is supposed to be the viscosity, although the program doesn't make very good news. It kind of makes them look like V's, so we just have to, remember that those are viscosities. Okay, so epsilon, diameter, and then what we're in Q, and what we're looking for here is the head loss due to friction. Okay, and really the key to all of these, rather than read out all of these things that are being given, is what are you looking for? Okay, and I'm going to explain to you why these three are so key. Okay, and I'm going to walk you through that real quick, and then of course I'm going to do an example of all three types. Okay, so HF, if you're looking for HF, okay, then the head loss due to friction is F L on D V squared on 2G. Okay, you've got Q right here. Okay, so Q, along with this diameter, okay, will give you that velocity. Okay, the length is always given. Okay, the diameter is given. Okay, so all you need to do is be able to get F. Okay, to get F, well, let's go over here. Okay, so to get F, we need to get it off this Moody diagram. So let's see, we've got epsilon and d. So we've got these two things here. That will give me this relative roughness, epsilon over d. And we can get the velocity. So then if I go down here, okay, I'm able to get the velocity because I have q and I have diameter, pi d squared on 4. Okay, I know d because it's given, and nu is given. So basically, these type 1 problems, I know this, and I know this, so then I can get this. Okay, so these type 1 problems, These are the easiest. Okay, you're going to want this one. Okay, now as a guarantee on your exam, final exam, you will have a type 2 or a type 3. Okay, that's a guarantee. Excuse me. Okay, now for type 2. Okay, to give you an idea here. Okay, now we're looking for Q. So if we don't have Q, what we don't have is V. Okay, so let's go and let's look over here and let's see what that means. Okay, for Moody. Okay, so I'm going to erase what we just did. Okay, so I'm going to go in here. Let's see, I'm going to zoom in if it will let me. Okay, the relative roughness. Well, we're good. I know epsilon and I know D, so I'm good at getting the relative roughness. However, when I go over here, I don't have D. Wait, no. I do have D. No. Yes, I have D. I do not have this. Can I have this? So then the question becomes, how do we figure out F over here, which can no longer have a check mark on it? How can I figure out F when I don't know this? Okay. And so it requires what we're going to call an iterative solution. So basically what's going to happen is you're going to end up guessing values. Okay, and you're going to guess a value, and that value is going to lead you to a better guess. And you're going to keep on using these better guesses to create even better guesses until your guess works. Okay, and I'll show you how that works in a second. Okay, and hopefully, okay, so that's the type 2. So type 2 is the second hardest. Okay, and then the last type where we don't have the diameter. Okay, so if you don't have the diameter, then you don't have V, and you don't have epsilon on D. Okay, so when you go to this type 3 one, okay, now over here you don't have diameter. Over here, okay, let's see. Come on. Okay, you don't have velocity because you don't have diameter, and you don't have diameter because you don't have diameter. Okay, so in other words, you're confused on this side and on this side. Okay, so it's going to be very hard for you to get the friction factor. Okay, so in this case, you're going to have to do another iterative solution, but it's going to be even more complicated iterative solution. Okay, so that's how they came up with these 3 types. And what we're going to do is I'm going to show you how to do all 3 of these. Now, the easiest is type 1, and I would say the hardest is type 3. Okay, so, but, that's, it is what it is. So we just have to do it, okay? So I'm going to teach you how to iterate. In the classes coming, they will teach you how to iterate using a spreadsheet. I could teach you how to do that, but I don't want to teach you how to do that because you're going to need to be able to do this on the FE, okay? So I highly recommend that you just learn how to iterate, and then you learn how to do it with the computer. Okay. All right. So we're gonna jump right in, and we're gonna do some examples. All right. So let's go over here and let's see what we got. Oh, we got buku Moody diagrams waiting for us. All right. Okay. Given. Okay, we've got some reservoir. It's got some amount of water in it. And basically what we want to know is how deep does that water have to be in order to get a flow rate of 10 CFS if we've got a 50-foot long pipe from here to here is about 50 feet. Okay, we know the viscosity of the fluid, and we know the pipe is concrete. Okay, so the fact that it's concrete basically means it's pretty rough. Okay, and so right off the bat, it's kind of like, well, I don't know if this is type 1 or type 2 or type 3. Okay, remember type 1 is basically HF equals question mark. Type 2 is Q equals question mark. And type 3, we're looking for the diameter. Type 3 is probably the most engineering-y one, okay, because this is kind of a design problem when we're looking for the diameter. This is a little bit engineering-y, right? This one is kind of like, that's more like class, okay? And so we don't really know which one we're looking for here. However, we do know right off the bat that this does look like an energy problem, an energy equation problem, because, well, we're looking for the height, right? And that has to do with elevation head. And there's clearly going to be an energy loss along this pipe, so we have to start thinking that maybe this is Moody, okay? And we note that there is a minor loss here that we are going to ignore for now, so I'm going to kind of dot it in red. But there's a friction loss along these pipes, okay, which we're going to consider. Okay, so let's just, I don't know which type this is, type 1, type 2, or type 3, but let's just kind of like play along and see what happens. Okay, so let's do the energy equation. And as usual, I want to pick points that I know stuff about. Okay, so I know a lot about this point, and it's on the atmosphere, so that means I don't have to worry about pressure. And I'm going to pick this point for my point 2, okay, because I know a lot about that point. I know its elevation. I know a lot of stuff, right? I know Q. I can get my velocity there pretty easily. So we're going to go ahead and we're going to work out of that point right there. So here's our energy equation. All right, so let's see. Let's go ahead and go through this. Both P1 and P2 go away because they're both on the atmosphere. Okay, so we're going to just go ahead with gauge pressure there. Z2, we're going to make the datum. Okay, which means that Z1 is going to be H. Okay, so this will be our datum going this way, datum. V1 is 0 because of the tank assumption. Okay, V2 is unknown, but we can get it. There's no pump between 1 and 2. There's no turbine between 1 and 2. And this head loss will expand into HF plus, so that's the friction loss, plus H lowercase l. Okay, so we got friction loss and we got minor losses. We can't do anything with the minor losses at the moment. So what we'll do is we will assume that is 0. Okay, I'm going to dot it because it matches with our minor loss. So we're just going to go ahead and get rid of that. Okay, so what does that leave us with? Okay, so that leaves us with on the right-hand side, on the left-hand side, H. So all of our energy on the left is basically potential energy equals, okay, alpha V2 squared on 2G plus HF. Okay, so all that potential energy is some of it's being used up into friction, and the rest of it is being used to power kind of the velocity here. Okay, so notice, basically we could solve this because V2 is pretty easy to get at because we have Q. Okay, because we have Q and we have the diameter of the pipe. So HF is the thing we're looking for. Okay, which means this is the easiest type of problem, and it's basically the most straightforward. Okay, so over here as an aside, let's go ahead and get that velocity, just like knock it out. Okay, so I can say Q equals V2A2. Okay, so if we do our calculation and we use the diameter of the pipe, then we get that V2 is 12.3 feet per second. And just, to check our alpha, because we also want to get rid of that alpha right there, let's go ahead and check to see if this is laminar or turbulent. Again, I'm going to pause it and just do it. Okay, so if I kind of plug those numbers in, those are all given. The velocity is not given, but we solved for it a second ago. I left it. I put too many significant digits on this on purpose. I usually like 3 significant digits. However, on Reynolds numbers, it's really never beneficial. I mean, really 1 is usually enough, but really just do 2. Okay, and you'll see why in a second. There's no real value to this. To having more than 2. For starters, it's all kind of a, I don't want to say hand wavy, but it's a little hand wavy. And anyway, you can see that this is much, much larger than, say, the 4,000 needed to be turbulent. Okay, so it's 3 orders of magnitude larger than that. So what difference does it make how many extra significant digits I have? It's not even close. Okay, A. B, when I use these numbers on the Moody diagram, you're going to see that I'm not going to be able to see that kind of precision anyway. Okay, notice that because it's greater than this, alpha equals 1.0, okay? Because it's turbulent. Okay, so what that means at this point is that this term right here is basically taken care of. So now we need to deal with this HF term. I mean, obviously I could plug all that stuff in and get that first term right now, but let's focus on this HF term. Okay, so the HF term, so if I expand this out, alpha V2 squared on 2G plus the HF. Well, that's FL on D, V squared on 2G. Okay, so what we need now in order to solve this, I know the length of the pipe, I know the diameter of the pipe, I know the v squared over 2g. So, I mean, if you wanted to, you could even simplify this. And you will see a lot of books do this. You don't have to, but you could write this like this, v squared on 2g, noting that v2 and v are the same in this case because it's just the velocity in that pipe. Okay, so you could write it like that if you wanted to. FL on D. Okay. But the key right here is we have everything in this equation except for that F. Okay. So how do we get the F? Okay, so every time you need the F, you want to be thinking Moody. So we're going to grab one of these Moody's and we're going to bring it down here. And we're going to go ahead and try to see if we can get that F. Okay, so here we go. Well, you know what? We'll just zoom in on it. Okay, so the first thing we need is we need the relative roughness. Okay, so if we look at it, we need this thing right here. Okay, so I need epsilon on D. Okay, so let's see here. Epsilon on D. Come on, punk. You can zoom out. What's our epsilon? Oh, they don't give us an epsilon. What they give us is they give us the fact that this is concrete. Okay, so what I'm going to recommend here is that we go over here and let's see. Okay, concrete, look here, concrete. Do we have concrete? We must have concrete. Concrete right here. Whew. All right, well, now it's done something to us really annoying, right? It didn't give us a single value for concrete. Now, note on a test, I will usually tell you what value to use. In this case, okay, if it gives you a range of values, what I recommend you do is you pick the one that you like, okay? So, like, for example, if I was given riveted steel right here, I would put 0.01 because that's an easier number for me to work with than anything than 0.003. I'm not going to choose like 0.03 repeating or something. I mean, you can choose anything in there. So what we're going to do here is we're going to choose, let's choose 0.01. Okay, that makes sense to me. I'm not sure why. Can I get you to go a little bit smaller? Okay, so let's do, or you know what, let's do 0.001. Okay, that's feet. Okay, we have to notice the units. And then the diameter of the pipe is 1 foot, and so epsilon over D is 0.001, unitless. Okay, so that gives us our relative roughness, check. Okay, Reynolds number. Oh, well, we already calculated the Reynolds number. Well, that's nice. Okay, 1.3 times 10 to the 6th. Okay, so we've got this. Okay, so now we're going to go ahead and we're going to solve for our F. Okay, so let's zoom in. All right, so the way we do this is we're going to start, and I'm going to kind of do this in a different color. Let's do this in green. Okay, black's not really going to show up too well on this. Let me zoom out just a midge so we can see the, there you go. Okay, so we're going to start, I like to start with the relative roughness. So 0.001, so that's right here. Okay, so what I'm going to do is I'm going to try my best to highlight that line. Okay, so there's that line. Okay, so now we need a Reynolds number. The Reynolds number is 1.3 times 10 to the 6th. Okay, so I'm going to have to erase this because I can't really see what's under that line. Okay. So let's see, what color will we use for that? Let's use some blue. It is the best color, let's be honest. Okay, so here's 2 times 10 to the 6th. Here's 1 times 10 to the 6th. So 1.6 is somewhere in the middle there. And look, it doesn't really matter, right? So if I go like right up in here maybe, it doesn't really matter. So we're going to go to about right there. And then what I'm going to do is I'm going to hit that spot, and I'm going to take a left-handed turn until I hit the y-axis. Okay, so we're going to go like this. Okay, obviously that's not perfect. That's sub-perfect. That's less than perfect. But anyway, so 0.1, 0.1, 0.012, 0.014, 0.016, 0.018. Let's say 0.019. Okay, and I think, let's see, when I did this initially, I got a totally different number. Right, because I had a slightly different value for concrete. Okay, so So we'll use that number, 0.019, so 0.019. Okay, if you wanted to, you could even put a 5 on there, but that seems like you're getting a little bit ridiculous. We can only know so well. Okay, so what we'll do is we'll zoom out and we'll take that number and we're going to use it. Okay, so what we'll do is we'll go right down here and I'll say H. Oh, I don't want to use blue. H equals 1.0 plus 0.019. Be very careful with this 0 right here. It's the most common error is that people forget to write it there. You'll see I'll probably forget to write it there as well. It happens. Okay, 50 feet over the diameter, which is 1 foot. Okay, v squared, 12.73 feet per second squared over 2 times 32.2 feet per second squared. Okay, so we plug all that in. And we get that the height of the fluid is 4.91 feet. So in other words, you need 4.91 feet in order to drive 10 cubic feet per second out of that 50-foot pipe. Okay? And that's it. Okay, so this is the straightforward one. And it's straightforward because you just kind of like, okay, what do I need now? What do I need now? And you just kind of work it. So this is called a type 1. Okay, right here. So that's the type 1. We're going to go in order. All right, let's go to the next example. All right, here we go. Water with a, what is this? Velocity of 1.13 times 10 to the minus 6 meters squared per second. Okay, wait, there's something weird going on here. What is it? Look, what is this going on? Right? Meters squared per second is a velocity. Okay, it seems to me that maybe, okay, that's supposed to be a nu. Okay, so notice if you got weird units, there's something going on. Okay, you always got to pay attention to your units. Okay, so this is the viscosity. Water with a viscosity of 1.13 times 10 to the minus 6 meters squared per second flows through a 0.3 meter riveted steel pipe with an epsilon of 3 millimeters with a friction loss of 6 meters. Find Q if the length of the pipe is 300 meters. All right, so I'm just going to kind of draw this real quick. By the way, I had a professor in grad school who used to always wonder why students were so adverse to drawing. And I agree with him. Okay, it's really not that hard. It's not going to take that long. It just kind of helps you get an idea of what's going on. So I highly recommend taking the moment to do this. Okay, so little roughness factors here is so it's 3 millimeters, 0.003 meters. Okay, friction loss of 6 meters. We know the viscosity, and we know that this thing is 300 meters long. Okay, 300 meters long. Okay, and we're looking for Q. Okay, so we know it's got a friction loss. That's HF is 6 meters. Okay, so this thing's got fluid coming in. It's got fluid leaving. And, okay, so this one's pretty easy to identify what it is, type 2. Okay, because we're looking for Q. It straightforward says find Q. But this one is a little bit interesting, okay, because the inclination is, all right, well, it tells us something about a friction loss. Okay, so our first guess here, and it's not even a bad guess, is to say, okay, well, let's use the energy equation. So P1 on gamma plus Z1 plus V1 squared on 2G plus, there's no pump, P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT, there's no turbine, plus the head loss. Okay, so if we were to try to do it this way, okay, we don't know the pressures. Let's suppose I make this 0.1 and I make this 0.2. I don't know the pressures in either location, so those are unknown. Okay, Z1 and Z2 are the same, so they go away. There's no pump. There's no turbine. Okay, the velocity at 1 is the same as the velocity at 2, okay, because the pipe is not changing diameter. And so what? I get P1 minus P2 on gamma equals the head loss, which, of course, we would split out into HF plus HL. And there's no minor losses anyway, so this is going to go away, equals HF. Well, there's no way for me to get at this P2, this P1, or this P2. Okay, so this is not very helpful. Okay, so not useful. However, I can do something a little bit more straightforward, which is I can say, okay, well, but I could just use the Darcy-Weisbach equals F L on D V squared on 2G. Will that work? Okay, well, let's see. We know HF. Okay, so this is known. The length of the pipe is known. Diameter of the pipe is known. V squared. Well, we need Q, so that's what we're looking for, right? So this is what we're looking for. 2G. So basically, we don't know two things. Okay, V squared and L and F, okay? And we're looking for this, but to get it, we need the F. Okay, cool. If you think back to the last problem, that seems very straightforward. So let's zoom over to our little Moody diagram, knowing that all we really need here is a little bit of F. Okay, so let's go over here and let's talk about how we're going to get F based on what we have. Okay, so relative roughness. Can we get the relative roughness? Epsilon on D. Okay, well, let's see. The epsilon is 0.003 meters, and the diameter is 3 meters. Notice it's unitless, so those cancel out. So I'm left with 0.3 meters. So this is going to be 0.01. Okay, cool. All right, we're cooking with gas. Let me go ahead and let me highlight that one. 0.01. Okay, that's this line right. Oh, no, that's not this line. Oh, all right. Okay, be careful now. Okay, it's this line. Okay, the number of zeros. They never do this in scientific notation. Moody diagrams are never in scientific notation, at least that side. I don't know why. It makes it real easy to make an error, and I just made one. Okay, so that's the line that we're playing with here. Okay. All right. Let's erase this so we don't confuse ourselves. All right, now what? Let's see. Now we need the Reynolds number. Okay, so the Reynolds number is the velocity. Well, that's what we're looking for. No, not in green, you punk. The velocity times the diameter, which we know, 0.3 meters, times the viscosity. Well, the bottom line is here, we don't know this. 1.13 times 10 to the minus fifth meters squared per second. Okay, so basically we can't solve that. So if we can't solve that, okay, so if we cannot solve this thing right here, okay, if I can't get the Reynolds number, then I don't know where to go up. You know, like if I knew where the Reynolds number was, and if I said, okay, well, I know the Reynolds number is right here. Let's just say it's like right here. Right, a bunch of pows. Okay, I can pow it up, and I can hit that line, and I can take a left turn, and I get my F, and then we're in good shape, you know? Because we could just straight up solve the problem then. Okay, well, maybe. Okay, so what we're going to do here is we're going to do this iterative process. And every time you see a type 2 problem, we're going to do the same sort of iteration. It's going to be the exact same order, the exact same things. The equations won't be the same. You're going to have to make the equation for the given problem. And so what I'm going to do right now is we're going to create the equations for this problem. But what you're going to do is you're going to guess an F. Well, let me zoom out and I'll kind of okay, let's see here. Where is it? Okay, here we go. So what we're going to do is we're going to do it right down here. Okay, you're going to guess an F value. Okay, from that F value, okay, you're going to be able to get a velocity using an equation, which I'm going to call equation 1. We'll label it when we get there. From that velocity, you can get a Reynolds number from equation 2. Okay, this incidentally is equation 2. We've already gotten there. And then from that Reynolds number, we're going to go and get F off of this Moody diagram. Okay, so we need some equations. Okay, so let's see here. So it's always going to be these things. You could have this particular thing you could have written right from the start. Okay, I need an F assumed, I need a V, I need an RE, I need an F from Moody. Okay, so the only thing we need at this point, well, first I'm going to simplify this equation because I want this equation to be easy to use. So just because I've already done it, I'm going to simplify this equation. All right, so then in order to do this iterative process, so this is called iteration, what we're going to do here is I need an equation that relates velocity to F. Okay, so this equation 1. And it just so happens that we've actually already got this equation. It's right here, look. Okay, so if I rearrange this sucker, okay, I can just, we can go, all right, let's rearrange this. And I get, let's see here, V, come here. Come on, you can write. You can do it. It's not that complicated. Come on. Okay, so if I rearrange it, there you go. All right, I can rearrange this to V equals 2G D HF on F times L, okay, square root. All right, now you might say, okay, that's cool and everything. And it is, but what we want to do is we actually want to make this kind of clean, okay? So I'm going to make this clean by, well, it's actually dirtier, but we're gonna basically plug in the numbers here, because what that's going to do is that's going to enable me to kind of, because I'm going to have to use this equation several times, so I want it to be easy, okay? So I'm going to go ahead and plug in the numbers. We got 6 meters of head loss, okay, over F, which we don't know what that is, and L. So what is L here? L is 300 meters. So F times 300 meters. Okay, so V equals, okay, if you ignore my error with the, obviously that should have been meters per second squared. I'm sure some of you caught it. Hopefully you didn't already send me an email about it. And here's our velocity. Okay, so this is going to be our first equation right here. Okay, so what we're going to do here, and I'm going to kind of walk you through it a little bit this first time, but we're going to go over here, and this is the part that people really, really dislike right here, is that you have to guess, you have to assume an F. Okay, now nobody likes that, because kind of like, well, I don't know what an F is. Like, you're probably sitting here right now going, well, I don't know, is an F 0.2? Is it 200? Is it 500? Is it 0.005? Like, I don't even know where to begin. And I'm going to show you right now where to begin. And I recommend you always begin at this spot. But first of all, here are the reasonable values of F. Okay, they go from 0.01 to 0.08. Okay, as long as you're within there, this is going to work out for you just fine. Okay. Second thing, okay, and here's where I get the easiest and best guess for this, is you see this whole region over here where it's flat? Okay, let's do this in red. Okay, you see this whole region where you've already got epsilon over d, right? You see this whole region where it's flat? Okay, in that whole region, okay, for that epsilon over d is 0.01. Okay, there's your guess. Okay, because that is the most likely answer, is 0.038. Okay, that is your best guess right there. Okay, and so that's where we're going to start. Okay, and that's a good guess, and that's what I'm going to recommend every time. But really, as long as you're in this range, it's going to work out for you. Okay, and I'm going to show you, I'll do this twice. And the first time I'm just going to do it my way. But I'm going to do it with this guess, which is going to be a very good guess. And then the second time, we'll just pick a completely outlandish wrong guess, and we'll just see what happens. Okay, so let's go down here. So that's my first guess, 0.038. Okay, 0.038. Okay, I'm going to go to this velocity equation over here, equation 1. Okay, right here. And I'm going to say V equals square root of 0.11772 meters squared per second squared divided by 0.038. Okay, and hopefully you can see right there why I wanted to write it like this, because it's going to make it a lot easier for me to work with. Okay, so the first time I do this, now granted, remember this is based on a guess, so this is not the actual velocity, it's a guess. Okay, so I get, so this is the first line, I guess, is 1.7601. So I'm going to go over here, 1.7601 meters per second. Okay, from that, okay, I'm going to use equation 2, and I'm going to get a Reynolds number. So I'm going to use this thing right here. I'm going to say the Reynolds number equals 26549 seconds per meter, okay, times the velocity, which is 1.7601, excuse me, meters per second. So the Reynolds number equals, okay, this ridiculous number, and of course, I left it with way too many significant digits, again, because I want to make the point that you're not going to need that many, because look, we're at 4.7 times 10 to the fifth, and I look over here, and let's see here, here's 10 to the fifth, here's 2 times 10 to the fifth, 4 times 10 to the fifth, 5 times 10 to the fifth, so let's use blue, and let's go, okay, 4 point, what did I say, 4.6? 4.7 times 10 to the fifth. Okay, so here we go, 4.7 10 to the fifth. So somewhere in there, okay, more or less, 4.7, and boom, look at that. I'm in the wholly turbulent area, okay, where it's not a function of the Reynolds number anymore. So basically I can just go right back along there. And, well, basically I should have gotten the same number as I got when I did that red. Okay, so obviously that's a bad drawing. But somewhere in there will be your good answer. So in this case, we don't even need to iterate, okay? But actually, let's go ahead and put that Reynolds number in there. So it's going to be 4.7 times 10 to the fifth, and I ended up getting 0.038, okay? Now notice there will be some play on this, and so I don't, you're not necessarily going to get it exactly right. Okay, now what if you had stepped in here and you'd guessed really wrong? Okay, so this is your answer right here. Or that's your friction factor. But what was the question? Oh, the question wanted Q. Okay, so we have to solve for Q. So then Q equals VA. So I think at this point we all know how to do this. So Q equals 1.7601 meters per second, because that's right there. Okay, times the area, pi, times the diameter, 0.3 meters squared over 4. Okay, so Q equals... Okay, so Q equals 0.124 meters per second. Now, I recommend, this iterative process over here, iteration, okay, it takes a little bit of time. And so what I highly recommend is if you're in an exam and you're just out of time, you set this iteration up by finding this equation right here, equation 2, and labeling it. You find equation 1 and label it. And then you say, iterate, and maybe the iteration is worth 2 out of 10, and you just say, I don't have time. So you do time, and so you say, assume, okay, V equals, 1 meters per second, an easy number. And you plug it in over here so you can still get these points over here. Okay, so maybe this is worth 2 points. Maybe the iteration is worth 2, and maybe each of these equations are worth 3. So just make sure that you can do that. I mean, you'll lose these 2 points, but at least you won't be stuck. Okay, so... in this case, this was pretty amazing. I got the right answer in the first try. This will not usually happen for you. Doesn't usually happen for me. So I'm going to show what happens if you get a bad guess. Okay. So let's suppose I'm not going to choose 0.01 because that's kind of like off the chart here. Let's assume that for F you chose 0.012. So you chose right there. Okay, so I'm going to do this again. And so I'm going to say for your first guess, you said 0.012. Okay, you just happen to be way off. Okay, so, and I'm going to kind of pause as I do these things. So what we're going to do, we'd go over here, and I would plug it into this equation right here. Okay, and what would come out would be 3.1321 meters per second, okay? So I would take that number, and I would bring it up to this Reynolds number right here, plug it into equation 2, and I would get 8.3 times 10 to the fifth. Okay, so now I would go to Moody Diagram, and I would use those numbers, or that Reynolds number, basically, 8.3 times 10 to the fifth. Okay, so here we go. And I'll use blue for this. So here we go, 8.3 times 10 to the fifth. Is that right? 8.3 times 10 to the fifth? 8.3 times 10 to the fifth. Okay, 8.3 times 10 to the fifth. Okay, here's 8. Here's 9. So 8.3 is just somewhere between those two. Right? It's not really going to be perfect. Boom. Okay. Oh, that's nice. Okay, it looks like that's going to ultimately give us our final answer because it's hitting right on that red, which, of course, depending on how I've done the red, if I've done the red exactly right, okay, 0.038. Now, I don't know that that's the answer yet, right? And the reason I don't know that is because what I'm looking for to know that I'm done iterating is that this number has to match that number, okay? So this becomes my new guess. So 0.038. Okay, so then what I would do is I would plug that in back into equation 1, and I would get 1.7601 meters per second. I would plug that into equation 2, and I would get 4.7 times 10 to the 5th. And then I would go back to the Moody diagram and get 0.038. Okay, and then I would know that I got it done. Okay, so that's if you have a bad guess. This is a bad guess. Okay, it's going to take you another line, basically. Okay, and it won't always be like that. Sometimes it could be, an extra 2 or 3 lines. But usually if you're guessing, if you're in a type 2 and you're guessing F, usually you're going to get there, worst case scenario, 3 lines. Okay. Okay, so that's the type 2. All right. All right, so we're going to go over here and let's see what we got. Determine the size of a clean wrought iron pipe. Epsilon equals, okay, so not the relative roughness of very little, 0.00015 feet, required to convey 4,000 GPM. Well, before we go anywhere, we're gonna get that into something we like. Okay, nobody likes 4,000 gallons per minute, so we'll change it into cubic feet per second, CFS. Okay, so we're going to convert 8.93 CFS of oil. Velocity equals 0.001 feet squared per second. Oh, feet squared, that's a viscosity. All right. Hang tight, man. Cool. All right, over a length of 10,000 feet with a friction loss of 75 feet. Okay, so determine the size. So we're looking for D. Okay, so this is a type 3. Okay, type 3 is another iteration. Basically, type 1 is no iteration. Type 2 and type 3, we're going to have to iterate. I'm going to tell you right now before we even start, this is, as soon as you see that, this is your iteration right here. Okay, it's going to be D assumed, epsilon on D, Reynolds number, Moody, and then D. Okay, and so we're going to have equations here. So this is going to be equation 1. This will be equation 2. That's Moody, and this is going to be equation 3. Okay, we have to figure out what those equations are. The equations are not going to be the same each time. I'm going to tell you right now, when doing this, when assuming a diameter, I recommend assuming an easy number. Okay, what's the easiest number of a D to assume without even knowing anything about the problem? I'm going to assume 1. Okay, now, depends on whether or not you're in the SI system or the English system. In this case, we are in the English system, so I'm going to assume 1 foot. Okay, now, why is this one more difficult? Well, I'm going to show you why it's more difficult by zooming in on this Moody diagram up here and noting what we have and what we don't have. Okay, so we have epsilon, check. We've got Q. Now let's go ahead and put these things in here. 8.93 CFS. Epsilon is 0.00015 feet. We've got the viscosity is 0.0001 feet squared per second. We've got length equals 10,000 feet. And we've got a friction loss of 75 feet. Okay, so if I grab all of that and I bring it over here, and I want to think about how this is going to affect us. All right, so here we go. All right, so there's kind of a lot to think about here. And it boils down to this, okay? Epsilon over D. Well, we don't know D, so I can't do this guy. Okay, Reynolds number. Well, I don't know D because it's what we're looking for. And I can't get V because even though I have Q, I don't have D. So I can't get anything for the Reynolds number. Okay? Oh, man. Okay, so this is a headache. Okay, so let's go back over here. And let's note that the problem with both of these is if I had D, I could get that. If I had D, I could get this, because if I had D, I would know D, and I could get the velocity, right? So the D is the thing that is kind of in our way, okay? Because that would allow me to get an F. Wait, do I need an F? How do I know this is a Moody diagram? Do we even think about that? Okay, well, let's see here. Well, we know there's a friction loss. Okay, so if I wanted to do the energy equation for this pipe, okay, well, we don't know D. Okay, we know the epsilon, so little roughness factors is 0.00015 feet. Okay, we know Q, so we know 8.93 CFS. Okay, we know it's oil, and we know that it's 10,000 feet long. Okay, so, and we know the friction loss is 75 feet. If we were to do the energy equation like we did the last one, just like I did in the last one, I wouldn't be able to get at the pressure between position 1 and position 2. So this, I wouldn't be able to solve this. But what I can do is I can say, oh, well, HF equals F, so this is Darcy-Weisbach, L on D, V squared on 2G. Okay, and that's how I'm going to try to solve this. The problem, of course, is I don't know D, I don't know F, and I don't know V. Okay, so this is pretty complicated. So what we're going to do here, okay, so what we're going to do is if we zoom down, and I've got this nice thing where I'm going to start doing all this, work. And so what I want to do is I want to grab this, right? I've already assumed a diameter, okay? I don't even have to know anything about the problem. I'm just going to assume one. And then what I need to do is if I know the diameter, I need an equation to get epsilon over D. Okay, well, that's pretty straightforward. The equation is epsilon over D. Okay, so that's equation 1. Equals, is the relative roughness is basically, let's zoom in over here. So equation 1 is that epsilon on D equals 0.00015 feet divided by D. Okay, that's equation 1. Cool. Okay, then I need a Reynolds number. Okay, well, equation 2 is going to be Reynolds number equals, well, let's see. This is a little bit more complicated, right? So the Reynolds number is V D over nu. Okay, but the V, in this case, we don't know the V, right? So I need to use Q instead. So V is Q over the area, pi D squared. Let me zoom in here. There's no reason to be this far away. D squared on 4 times the diameter divided by the viscosity. Okay, so let's see, that's going to be, so we bring the 4 up, so it'll be 4Q. One of those D's is going to cancel. So we're going to get pi nu D. Ooh, nudie. All right, anyway. All right, so the Reynolds number is going to be 4 times Q, which is 8.93 CFS, divided by pi times nu, which is some really weird number, 1 times 10 to the negative 4th feet squared per second, times d, which means, okay, so simplifying, we get something that looks like that. Okay, so now we've got an equation 2. Okay, so equation 3 is to use the Moody diagram, so we've got that ready to roll. And then the last thing is I need an equation, if I have F, to get D. Okay, fortunately I've already set this up over here, or I started to set it up, which was this equation, which is going to get really ugly. So I want to solve this thing for D. Okay, so the easy way to do that is to bring the D up and get F, L on HF, V squared on 2G. Problem is that's, it seems like that's what you want to do, but the problem is there's a D hidden inside of this V, right? Because that V is Q on D. Okay, so we're not actually going to do it the way that I just did it, so let's erase that, okay? So what we want to do is I'm going to say HF equals F. L on D, that V squared becomes Q on pi D squared on 4 squared over 2G. Whew, that's going to get sloppy, right? So HF equals F, L on D, Q squared. Let's see here. There's a 16 that's going to come up here. We're going to divide that by that 2, and so that's going to become an 8. Right? And on the bottom, we're going to have, let's see here. We're going to have pi squared, D to the 4th, and G. So HF. I know this is complicated, right? It's a little annoying. It's a lot annoying. But there's nothing we can do about it. F, Q squared, L. There's an 8 out here over G pi squared D to the 5th. Okay, so if I rearrange this sucker, that D is going to come over here, and we're going to have a 5th root of 8 Q squared FL. I know I keep changing the order. I don't really know why I keep doing that. G pi squared HF. Okay, and that is going to be our equation. But again, because I might have to do this several times, what I want to do is I want to make this a little bit simpler. 5 over the square root of 8. Q squared is 8.93 CFS. We'll square that. The F is unknown, right, because that's going to come out of the last equation. The L is 10,000 feet. Here's our F, divided by G, which is 32.2 feet per second squared. Okay, pi squared, HF is 75 feet. Okay, so D equals the 5th root of, okay, and this is a good time to check our units. So we've got cubic feet squared, so that's feet to the 6th per second squared, times feet, divided by, let's see, on the bottom, we've got feet squared over seconds squared. Okay, so these second squareds are going to go away. This feet squared is going to get rid of this one, and it's going to turn that one into a 5th. So we end up with feet to the 5th. Feet to the 5th, and we're taking a 5th root, so that means that we've got the right idea here. Okay, so I've got this equation right here, and for simplicity, so this is going to be our equation 3. So for simplicity, I'm going to put it up here so that I can use it a little bit easier. All right, so all that's left now is to iterate. I've already told you what the first guess is. Okay, so I'm going to put in 1 feet. So now we're going to go equation by equation. So I'm going to go to equation 1. I'm going to go up here, put in 1 foot. I can do that in my head. Maybe I'll make my first guesses in blue. 0.00015. Okay, it's unitless. So I'll go over here. I'll go ahead and write that in there. 0.00015. Okay, now I need to get the Reynolds number. So I'm going to go up here. Again, I can do this one in my head because I chose a nice easy diameter, okay? And that's why I recommend choosing an easy one. 1137, well, it's easy, right? So this one's unitless. These are both unitless numbers. And for simplicity, I recommend 1.1 times 10 to the, let's see, 1, 2, 3, 4, 5, 10 to the 5th. Okay. And so now we're going to go over here, and I'll say, okay, 1.1 times 10 to the 5th. Okay, now I need to go to the Moody diagram, because I now have the 2 things I need for the Moody diagram. So we're going to zoom in here, 0.0015, 0.3015. Okay, always be careful with your number of zeros here. You will see me make this mistake. So, oh, this one kind of sucks, right? 0.001, 0.002, so it's going to be somewhere in here, right? So you just have to do the best you can. Okay, so it's somewhere between those 2 solid lines. And it's going to kind of do what we do, which is like, that's maybe the best we can do, right? And it's not going to be perfect. Okay, and there's some leeway when you're grading, but that's the best you can do. Okay? All right, so now we know that. Okay, so, and what's my Reynolds number? 1.1 times 10 to the 5th. Okay, so here's 10 to the 5th. So so here's 10 to the 5th. So 1.1 is maybe right in here. It appears I'm running out of battery, which is awfully annoying. But anyway, we're going to go up like this. right there. And then we're going to take a left-handed turn. Okay, and we're going to go like, I don't know, like this. Okay, and that's my first F, 0.022, 0.02, almost 0.024. Okay, so we'll go with 0.024. It's not, especially this first number is not really that important. 0.024. Okay, so now I'm going to plug that into this one. Okay, and let's see what we get. And you get an error, right? Well, I mean, the error was earlier, right? And you probably caught it and I didn't. Okay, hopefully you didn't send me an email about that yet. All right, so this number has an extra 0 on it, right? This one has an extra 0 in there. So let's go back over here and let's fix that, okay? I make this error all the time, okay? Hopefully you will be better at this than I am, okay? So we're going to go like this. And the Reynolds number will remain the same, so there's no reason to mess that work up. But let's go here, and we're going to go 0.00015. So, oh, something's happened. Okay, so it's going to be right in here somewhere. Okay, so we're going to go like this. Okay, and there we are. Okay, so here's our spot. Okay, so when we go this way, right, let's go like this. Okay, 0.018 looks like, or 0.019, I think, 0.019. Okay, so let's go over here. Let's go down here, over here to our F value here. And we'll erase that. 0.0. Come on, you can do it. 0.019. Which, of course, leads me to this equation for D, which, incidentally, when I plugged these numbers into my calculator, I had an error here. And this was the bigger error that I was missing. So we're going to pretend that when I plug those numbers in, I plugged them in correctly and didn't get this number. Instead, I got, the correct number, which is 200 and, this should not be in blue. 267.66 feet squared. Okay, so in blue, apologize for those errors. If I plug in 0.019, I end up getting for my F, I end up getting 1.3844. We're at feet per second. Okay, so that gives me a D of 1.3844 feet per second. Okay, are we done? Well, let's see here. I started with an assumption, not feet per second, feet. Oh man, I'm really struggling today. All right, so if I look down here, okay, I started with a guess of, come on. Okay, so I started with a guess of 1 foot, and I ended up with a diameter of 1.38. Okay, so these do not line up. So we're going to do another line, and I'll do this line in green. Okay, so I'm going to start with 1.3844 feet. That's awfully specific. Let's just go with 3 significant digits. I think we're going a little overkill here. So now I'm going to do E over D. So I'm going to go up here to E over D. So E over D in this case is going to be 0.0015. 0.00015 divided by 1.38 equals 0.0, I mean, it doesn't really equal that number, right? Those are different numbers. 0.0010 870, okay? 0.0010870. 0.0001080. Okay, so now we need to get the Reynolds number. So the Reynolds number, okay, I'm going to plug it in. I'm going to plug it into this equation right here. I'm going to do, okay, so the diameter is 1.38. So I got 113700 divided by 1.38 equals 82,391. 391 unitless. So 8.3 times 10 to the fourth. Okay, so we're not too far off the old Reynolds number, so that's a good sign. So let's go back to our trusty Moody diagram. So we're going to go 0.0001, 0.0001. Okay, so now we're basically right on this solid line right here. Let's zoom it all the way in so we can see what we're doing. Okay, and obviously if we were up in this region, they'd be indistinguishable. Okay, and our Reynolds number is 8.3 times 10 to the fourth. So 8.3 times 10 to the fourth, so we're somewhere like right in here. Okay, hard to distinguish between 8 and 9, but we'll go, come on, get out of here. Nope. Okay, so we're gonna go somewhere in here. Go up to that green line, take a right, or left, excuse me. Okay, it looks like we're gonna get a slightly different value. Okay, so let's call that 0.019. Excuse me, 0.0195. Is that right? Yeah, probably 0.0195. Okay, 0.0195. So we can see that we're pretty close at this point. Okay, I'm not gonna, well, maybe I will do the last line here. Let's do one more line. Okay, so let's, oh wait, we need to solve for our diameter. So if we plug that in here, I'm gonna get, let's see here. 267.66 times 0.01195 equals, raise that to the 0.2 power, and we're going to get 1.3916 feet. Okay, as you can see at this point, probably these are close enough that I'm not even going to get distinguishable answers. But I'll go ahead and I'll just kind of pause it and do the work for you, and we're going to see how this works out. So the first thing is in red. I'm going to go 1.39 feet. Okay, so if you do this, then you end up basically getting to a point where you're matching, right? You can see these numbers right here on the Moody diagram are going to be very hard to distinguish from the numbers the line before. Okay, and if we zoom in to the Moody diagram, you can see I kind of did it in red. So here's that. That epsilon over d, the relative roughness, which is right on top of the other one. Like I can't tell the difference. And then for the Reynolds numbers, they're so close that essentially they're the same. Okay, so when we go over here, we end up with the same spot. And you can see, if you look at the transition from blue to green to red, how we're kind of honing in on the correct answer. So if I had chosen something, a really, really bad guess, and I had begun, I don't know, way over here or something, you can see that I would have had farther to go, but probably what would have happened is I would have jumped from this point right here to maybe like this point, and then on my third jump, I would have been right on it. Okay, so it doesn't really take a whole lot of iterations usually to do this. Okay, so then the last thing is we have to remember, well, what did the question ask? Okay, we've gotten all the way to the end. It wanted to figure out. Determine the size. We're looking for D equals question mark. Okay, so if we go over here, we can say, well, so D equals 1.39 feet. How many is that? What is that in inches? So if we take that number, 1.39, we multiply times 12, that's about, what's that, 16.68 inches. Okay, you probably don't sell that. So probably what you're going to want is you're probably going to want an 18-inch pipe. Okay, it's probably your answer. Okay. Anyway, for a test, obviously, I don't expect you to know what is commercially available, although probably most of you intuitively would understand they don't sell a 16.68-inch pipe, okay? But they might sell a 16 or a 17, but basically, factor of safety, you want to be a little bit large, okay? So anyway, I guess if I gave you, that these were the pipes that were available, you should pick the next biggest one. Okay, so that's all I got for today. That's an hour and 4, so that's a pretty long lecture. This is just going to be a one-off. We're not going to have a B part. So anyway, take care of yourselves, and hopefully this helps. I think there's another lecture on this if you're confused. I did last semester. The only thing that I would warn you on that one is that for that one, I was using a different textbook, so this epsilon on D, I used KS on D, and that's because that's what that textbook used. And so for that textbook, KS is epsilon. But then to be confusing, they said epsilon equals. So for that textbook, this is a relative roughness. Okay, and this is the sand roughness length. This length, okay? And it's just a different textbook, but it all works the exact same. Okay? Oh, and if ever you need these epsilon values, these roughness values, okay, you can get these from a textbook. Okay, this particular Moody diagram has them on it right here. Okay, but notice that it only has the ones for the English system. Okay, it does not have the metric system. Okay, in your textbook, it looks like it's on page, oh, I lost a page. Anyway, there is one in your textbook. It's kind of on the side of the margins. I don't have where it is at the moment. Okay, but it's in there. Okay, so find it in your textbook, tab it, because you're definitely going to need it again. Okay, that's it, and have a good day. All right, bye.